Hello and welcome to our webinar for today. This webinar is being brought to you by the Water Loss Specialist Group of the International Water Association in coordination with Guterman Inc., leak detection equipment manufacturer. My name is Eric Galosi. I'm the commercial director for Guterman here in the United States. I am located in Harrisburg, Pennsylvania. And with me today, presenting, is our customer success associate, Max Ward. Max, you want to say hello?
Hello, everyone.
Max
Hey,
is, yep. Go
someone's drawing on the screen, I think.
ahead. Yes, someone is drawing on the screen. So,
That.
we've got an anxious group today to learn a little bit about leak detection. So we'll give another minute or so to let more people sign in. Max will be responsible for keeping this webinar running smoothly as we run through the presentation. We're going to do about 45 minutes worth of information. And then we'll follow it up with about 15 minutes of question and answers. I think Max has already sent out an initial chat. You'll submit your questions via the chat, and we'll go through those as towards that last 15 minutes of our hour here today. So again, thanks for joining us. We're going to provide you with some fantastic information on the basics of leak detection. We affectionately call this presentation Leak Detection 101.
Eric, do you want to open your video so people can see you present?
Oops, sorry.
If that's something you want to do.
No, that's okay. We'll just show the screen. I'm going to run right through the screen. You
Sounds
can
good.
see the screen. Okay, very good.
Right.
I'm going to. Okay, I think everyone's settled in, so let's get started here. Real quick overview of the Guterman Company. We have offices located throughout the globe. I'm coming to you, and Max is coming to you from the United States. Max is up in Newmarket, New Hampshire, where our main U.S. office is located. The Guterman headquarters is located in Switzerland. We have a dedicated staff of North American team, and so we're here to provide all the services that Guterman offers to the United States, to the North American market. And we have a full line of loyal and satisfied customers. A couple of them you're going to see on the screen right here. We will actually have a case study from one of these customers towards the end of our presentation today. So without further ado, let's get started with Leak Detection 101. The general overall principle of effective leak detection is to what we call the LLP process: localize, locate, and pinpoint. You're going to start and localize your water loss down to a specific area or zone, a district metering area, or your sub-metering divisions. You're then going to locate that leak. You're going to locate the position of that leak using leak noise correlators and leak noise loggers. And then finally, before you dig, you're going to pinpoint precisely where that leak is located using your ground microphoning and listening stick equipment. And then with this localize, locate, and pinpoint process, following this process, you're going to ensure the most accurate location of your leak locating and thus you're able to dig a accurate hole and a quite small hole to get down to the leak. But before we get into the equipment and the process of leak location, let's delve into a little bit of the leak detection theory. How we can pinpoint a leak on a length of pipe. Um, what we're using with our acoustic equipment, our noise loggers, is we are searching for the sound that the leak is making on the length of pipe. There's a lot of different sources of pipe noise. Um, Obviously, leakage being the source that we're looking for. There's also consumption, the flow, and the meters. There's noise created by PRVs. There may be noise created by close proximity to another pipe. Changes in pipe diameter will cause um, a source of noise. Um, Obviously, water pumping. Electrical hum of pumps and transformers will create noise. Air conditioning units. So your water pipe network is capturing and hearing a lot of noise. Our job is to basically discriminate between the good noise of leakage and the noise that isn't leakage, all the other sources that I just mentioned there. So how do we discriminate between a leak noise and a non-leak noise? Let's take a look at how noise is created on a length of pipe from the leak. Um, Noise on a length of pipe, and when I talk about the length of pipe, I'm talking about the pipe wall, is created when you have water escaping the pipe via a leak, pinhole leak, a crack, a poorly fitted bell joint, will all create an avenue for water to escape the pipe. And it's that water, as it goes from a high pressure environment inside the pipe to a low pressure environment outside the pipe. And it's that pressure drop, that pressure differential that the water experiences right at the point of rupture on the pipe. That pressure differential creates the vibration, that is the sound, that is then carried via the pipe wall throughout the pipe network for a given distance. The objective with our electronic listening equipment, our correlators and our sensors, is these sensors are placed at various locations along the pipe network at easy to access points such as your valves and meters and hydrant valves. And the sensors are picking up or listening to the vibration that is running down the wall of the pipe, that it was created by the pressure differential at the point of rupture of the pipe where water is escaping from a high pressure environment to a low pressure environment. There are a number of variables that affect the leak noise and the quality of leak noise. High pressure will create a better sound, a louder sound, a more distinguishable sound. Um, that pressure differential, the higher the pressure differential, the better the sound is going to be created. As that pressure differential lowers, lower water pressure, that sound becomes more muted and less audible. A small rupture will create that higher and maintain that higher pressure difference, as opposed to a larger rupture in the pipe will create a less of a pressure differential. Pipe material also affects how the sound and how well the sound travels down the network, which is what we need to be concerned about because our sensors will many times be located a distance away from the actual point of the leak. Your steel, ductile iron, and copper will transmit the sound fairly well. As the pipe material gets softer, down to AC, lead, and then finally your PVC and your poly pipe, That softer material absorbs the energy of the sound, of the vibration, thus not allowing that vibration or the sound to travel as far and as well as your steel and ductile iron pipe material does. And then also there we can take a look at the frequency range. Our sensors are listening to the sound, but really what they're looking at, and really what our software is analyzing, is the frequency of the leak. The leak has basically two dimensions. It's got an amplitude, which is the loudness or the decibel level of the leak, and it's got a frequency, which is roughly the hum or the pitch of the sound. And that hum and pitch is measured in hertz. And typically, we know that certain pipe materials transmit sound in certain hertz range. The backfill, the dirt that the pipe is sitting in, also affects the quality of the sound. A porous backfill allows water to, a porous backfill allows water to drain away quicker, thus maintaining that high pressure differential. A non-porous backfill will capture and hold that that escaped water in a cavity, which will over time create back pressure. That back pressure lowers the pressure differential between the water inside the pipe and the water outside the pipe, and thus, as we all now know, that lower pressure differential negatively affects the quality of sound that is transmitted down the pipeline. So you can see that small pipe rupture creates a high pressure differential, which creates a loud and high frequency noise. And this is the ideal noise to capture to do your leak detection. A larger rupture or a main break or a complete split of the pipe where you lose pressure inside the pipe, that pressure differential between inside and outside diminishes greatly, and you have little to no noise propagation down the pipe. What this means in a practical sense for your leak detection activities is that do your monitoring to capture the leaks when they're small. The sound created by a small leak is ideal for capturing and pinpointing your leaks. But not only that, but it's also more ideal to do your repairs. It's a lot easier to repair a pinhole rupture in a pipe than it is to repair a mainline break. So taking a proactive approach and capturing those leaks when they're small pays off multiple times down the line, all the way through repair. The pinpointing of a leak is actually a mathematical equation. Our software in the leak detection equipment undergoes and takes the data that is recorded from the sensors and does a mathematical equation of that data. In this example here, you can see that sensor A and sensor B, or your two sensors, are placed at a distance along the pipe. The leak is creating that sound wave. As I mentioned, the amplitude is the height of the wave, the frequency is the length of the wave, and that wave is traveling to the sensors. The sensors are doing nothing more than just recording that sound wave. If both sensors then, once the data from both sensors is compared and analyzed, if that sound that they're hearing has a similar hertz range, that means you've got a correlation. A good correlation will mean that the two sensors are hearing similar sound or a similar hertz or a similar frequency emanating from the source of the noise on the pipe. A poor correlation is the two sensors are not hearing the same frequency. They may be hearing other sounds, but the sounds that they're hearing are not a match. And therefore, we can easily determine then that this is not a correlation, or it's not sound coming from a single source. That single source would create a nice peak or a good correlation.
Hey, Eric?
Dissimilar. Yes, yes.
Sorry, your audio is a bit scratchy, which is something we haven't really encountered before. So I wonder what's
Okay.
going on your end. Is there any way to?
Let me see. Hold on.
Might just be other Wi-Fi devices around you.
Is that better?
It's better now. It keeps going in and out.
Okay.
So we'll see how
Okay.
that goes.
Okay. Very good.
I'll let you know. All right. Sorry about
Okay.
that.
Thanks. That's all right. And the actual pinpointing of the leak on the pipe is a mathematical equation. And what you see in front of you is the actual mathematical equation that we use to locate the leak on a length of pipe. All of the variables in here are easily obtainable. We either obtain them through measurement, we input our pipe material and diameter, and the sensors provide us with the time delay. So the L is your distance, which would be the distance of the leak from sensor A and sensor B. That sum, that leak distance, is calculated by taking the total distance between your two sensors. That is an input done by the operator as he measures between the two sensors that have done their listening and correlation. The V value is the speed of sound based upon the pipe material and diameter. Our software, your leak detection software, will provide those speed of sound values based upon the material and diameter of the pipe that the operator puts into the software program. And then the time delay, that is the delay, the difference of how long sound from a single source is reaching the closer sensor as opposed to the farther sensor. That time delay variable is provided with the loggers in the sensors. That is the information that the sensors are providing to the equation. So with that simple equation, you can mathematically calculate the precise pinpoint location of the source of sound on the length of pipe.
Eric, your audio is still a little off. Maybe try the connection to. Do you have a corded connection between your headset and the computer, or no?
I don't right now.
Okay, maybe it's the Bluetooth. It does go in and out, so
Okay.
hopefully it's not too bad. All right, carry on.
Okay. Okay. Okay, with correlation, with pinpointing, as you can see in the example we're looking at, the accuracy of your leak is greatly enhanced with the placement of your sensors. The objective with correlation and location of your sensors is to place the leak in the middle third between your sensors. When the leak is too close to one sensor or the other sensor, you introduce a greater variable between the time difference between the two sensors. And that variable or that inaccuracy of time difference may be the result of repair clamps on the pipe, old pipe, segments of pipe that you may not even know are underground when you are putting in your pipe data. You can lessen those differences and those variables if you position your sensors, if you position the leak in between your two sensors. So the example that we're showing you here is if you do have a correlation close to one sensor, it's wise to reposition your sensors so you're placing the leak in between the two sensors, and thus you're going to increase your correlation accuracy significantly. Also, sensor placement plays a vital role in pinpointing accurately the location of your leak. And you see in the first setup here, we have two sensors on a length of pipe at a T, and the leak is actually located on the T length of pipe that is joining the main length of pipe that is being monitored. In this situation here, your two sensors will only correlate to the point on the pipe where the common sound is emanating from. And in this first setup example, it's emanating from the T. An operator would now understand that I'm getting a good correlation at the T, but I need to ensure that my leak is not at the T, or perhaps maybe on the other length of pipe. So in the second setup, a sensor is moved to a new location, and now you have the ability to correlate and position the leak in between the two sensors. And now a leak can be accurately pinpointed on that length of T pipe. So when you're looking at your correlation graphs, a sharp peak is going to represent a good correlation with a high level of accuracy. And a broader peak will indicate a lower accuracy or a poor correlation, which may be the result from less than ideal sensor placement. And when you're using a correlator, never dig a hole based on the correlation peak that is close to one sensor or the other. Always try to reposition that leak in between the two sensors in that middle third, and thus you're going to establish your ideal and your best location for the pinpointing of the leak. You also do want to be aware of exact center correlations. A correlation that puts you exactly in between your two sensors is a definitive indicator that there may be a fault of a faulty sensor, or one of your sensors is off. When one sensor is only doing the correlation and there's no data coming from another sensor, your software program will see that as a center correlation, a pure perfect leak in between your two sensors. So although you are trying to position that leak in the middle third of your two sensors, you do want to avoid that exact center correlation. And as I mentioned earlier, that Manhattan skyline where you have where you don't have a clear peak, that's an indication that the two sensors are just not hearing the common sound. They may be picking up other sounds on the pipe, but there is not a common enough sound emanating from a particular point on the pipe to generate that good leak score and that leak peak. So now we have a general idea of how the sensors are picking up the sound. We know the sound is created by the pressure differential of water escaping a high environment inside the pipe to a low pressure environment outside the pipe. That sound is created as a sound wave, which has an amplitude and a frequency. That sound wave is transmitted traveling down the length of the pipe. Your two sensors placed on the valves at various points along the pipe network collect that sound and record that sound. The software then analyzes that sound to determine if there's a similar frequency between the two sensors that have collected the sound. If there is, you've got good correlation, and you can begin to develop your peak. If there isn't, you've got the Manhattan skyline. If a good peak is generated and you have correlation, the user then needs to put in the distance between the two sensors, the pipe material and diameter, and now you have all the variables necessary to do your mathematical equation to pinpoint precisely on the length of pipe where the leak is emanating from. So now we got the basics, the theory of leak detection. It's time to now go out and find some leaks. And what you want to do is to do an effective leak detection program, you want to set up your correlation area. Where am I going to go out and do my leak detection? I'm going to locate all my possible access points in the area. We have a general ranking that I like to follow. Your mainline valves are the best location for your sensors. The hydrant valve is next best. I've done it on the hydrant, putting sensors right directly on the hydrant. A valve key on a key that is making contact with the valve underneath the street is also good. I've also put my sensors on water meters. Once your sensors are placed, you also, now the operator has to input the first dimension or the first variable, and that is the length between the sensors. Accurate wheel measurement will go a long way in making your pinpointing accurate. So a good wheel and a straight measurement from sensor to sensor. And then finally deploying the sensors. Make sure that you have good magnetic metal to metal connection between the sensor and the valve. Even a little bit of dirt between the sensor and the valve will stop that or muffle the sound that the sensor is picking up, and it won't get the good frequency, clean sound necessary to hear the leak. So a simple cleaning off of the valve, removing the dirt, lowering the sensor down, you'll feel the metal to metal clink or the magnetic connection. Gilliam manufactures a full line of electronic leak detection equipment. Sensors to capture the sound of the leak is basically all we're after here. And let's take a look at some of that equipment. What that equipment does, there are two camps of leak detection. There's a reactive approach and a proactive approach. Reactive approach is basically, I've got water bubbling up on the 100 block of Elm Street. I need to go out there right now, pinpoint it, so I can dig within the next hour or so. You know you have a leak in a particular area. There's water bubbling up. You've got low pressure customer complaints. You know exactly where you need to go in your system to find the leak, dig the leak, fix the leak. That would be your reactive approach. Your proactive approach is more of a, I've got a lot of water loss in my system, but I don't know where it's going. A proactive approach would be the ideal method for you to address that water loss, using multiple sensors placed in an area, a neighborhood, a metered area, to allow them to do their sensing, allow them to do their listening, retrieving the data and analyzing a much larger area to see if you have leaks there or not. The reactive leak detection, again, you're finding a known or a suspected leak by walking the system, listening to the valves. It's going to be more of a hands-on. The operators at the leak site investigating and using the equipment to find a leak in real time. And this is the line of equipment that you would typically use for that reactive, real-time, hands-on, middle-of-the-day leak detection activity. Your proactive approach, finding unknown leaks. I have a lot of water loss, but I don't know where they're coming up. You're systematically canvassing the system, looking for all of your leaks. Leaks that are occurring on valves, hydrants, mains. The goal of your proactive leak detection is to hear those small, non-surfacing leaks. The leak before it becomes a large problem. Again, as we learned earlier, it's these small, non-surfacing leaks, these small leaks that do create excellent sound for your equipment to pick up. And then finding these leaks when they're small. You now have great control over how and when you repair those leaks. You have the knowledge that a leak exists on at a particular point in your system. You can document it, and now you can fix it under your own schedule, armed with the knowledge that the leak is there. Proactive leak detection is typically performed overnight, allowing these typically smaller sensors to have the highest ability to hear the leak. It's typically at those overnight hours that your system pressures are its highest, your service draws are reduced, your system pressure begin to increase, and now we know too that that higher system pressure creates a better environment for the sound and for the sensors to capture that sound. So now you have the theory, the basics of how sound is created on a length of pipe, how we capture sound and to pinpoint, to correlate and pinpoint. The two main strategies for finding leaks, reactive or proactive. And now you have a whole host of equipment on the market for you to use to accomplish that goal. You now have all the tools necessary for you to create an effective, efficient, and successful leak detection program. Your leak detection program is going to utilize your equipment effectively. You're going to maximize your crew's work hours. You're going to find and pinpoint your leaks. And then the bottom line is you're going to decrease your water loss and increase your revenue. Your equipment purchase will have an immediate return on investment. What you will be doing is reducing the run times of your leaks. You're going to reduce the amount of time that operators are out in the field doing leak hunting. You're going to gain an increased knowledge of your distribution network. You're going to raise awareness. You're going to know that a leak exists before it becomes a major emergency. You're going to reduce the amount of overnight and emergency call-outs for your leaks. You're going to be repairing a smaller leak too. That will reduce your the amount of money spent on the leak repair. We have many case studies to support the efficiency of well-planned water leak detection program. And here's one right here from Birmingham Waterworks. And there are many resources available for you to help to do your water auditing, so you can track those monetary, the real value of your leaks. And then now you've done your leak detection, you've found your leaks. There are a lot of statistics that with an effective leak detection program, your system should mirror some of these gains. But also documenting and recording your activity is going to be just as vital as going out and doing the leak detection. The AWWA publishes and offers the water audit. The chart that you're seeing here represents the thought process or the process of documenting and monitoring your water loss environment, with the goal of reducing that non-revenue water. Looking at the chart here, the real losses, yellow box at the bottom of the chart, that indicates your leaks. So that all of those real losses, your leakage on transmission and distribution mains, the leakage and overflows at utility storage tanks, and your leakage on service connections are all leaks that you can capture through proactive and reactive leak detection. And that will go a long way to reducing that non-revenue water and increasing your revenue water. And here's an example of what I'm talking about with using the AWWA standards. So that sums up the leak detection 101. Again, you're establishing an effective leak detection program to capture both of those emergency reactive leaks, as well as your proactive non-surfacing, hard to find water loss created by those hard to find or non-surfacing leaks. We have some great case studies. And I'm going to share with you one simple one here. In Dewshore, Pennsylvania, right up the road from me, the fine folks at Dewshore put together this great little case study for us. They put out 2 sensors. They actually, I was part of this this leak detection effort. They didn't even know that they had a leak, but they wanted to begin using the zone scan sensors. And they knew that they had a length of pipe that ran through a wooded area, as you can see on the satellite view on their zone scan net correlation report. So they started by putting 2 sensors at their 2 access points. And as you can see, they actually located and pinpointed a leak just using those 2 sensors. And it was one overnight deployment. And lo and behold, a leak was found. They went out and fixed the leak. It was a crack around located in a 4-inch ductile. They had 130 PSI system pressure. What's very interesting is prior to repairing the leak, they had 2 wells in operation. With this one leak, they were able to turn off one of their wells. Now, Dewshore's a fairly small little community, a couple thousand connections. But by turning off their 2 wells, or by turning off the one well, they had estimated over 12 million gallons of year lost. They did the math. They figured out not only the water, but the chemicals, the electricity, all the savings that they incurred from being able to shut down one of their wells. And they came up with this cost savings of $75,000 a year just by putting those loggers out one night and finding an unknown leak. So that's a great example of finding an unknown leak, repairing it, and although this is an extreme example of saving resources from finding a leak, it's an example of what can be achieved through an effective leak detection program. So that wraps up the presentation part of the program. I'm going to answer, I think we have some chats. So I'm going to open up my chat here and take a look at some of the questions. Are we doing okay, Max?
Yeah, we're doing okay. Steve Gilliam has answered a few questions already in chat, so if you want to give him an introduction.
Oh, okay. Okay. I apologize for the sound. I think
it was
I
better,
did get
yeah.
a little. Okay, I did get a little internet connection weak pop up,
Hmm.
but I tried to. Yeah, there's. I think it was just weak internet here, which is a sign of the times now and then.
It could have been
Um,
it could have been me too, but
let's.
we figured it out. So, yep.
Okay, let's see here. I'm going through the chats. A good one I'm seeing is how to define the distance at which the sensors should be placed. A very common question. You've got sensors, you've got a system, and you've got leaks. Well, how far do you put your sensors? Um, Again, your sensor placement is going to be dependent upon the type of material of pipe and to a lesser extent the diameter of the pipe that you're doing your surveying on. Ductile iron and cast carries the sound very well. PVC and poly, not so much. And then AC and copper sort of in between there. So um, if you know what type of material you're measuring on, you can place your sensors accordingly. Um, when you're listening on ductile iron and cast, having these sensors 7, 8 to 900 feet apart is quite common. At 800 feet apart, and a leak on ductile iron pipe in between these two sensors will certainly pick up the sound of the leak. What you are trying to do and what you are ensuring yourself with the placement of the sensors, and in order to get correlation and pinpointing, both sensors need to be hearing the sound. So you want to ensure that both sensors, or if you're using more than two sensors, that you're giving your sensors the best opportunity to capture that sound. Sound doesn't travel nearly as good on plastic and poly. It's a softer material. The material absorbs the energy of the sound wave, and thus the sound wave doesn't travel as far. So therefore, you need to put your sensors closer together. On PVC pipe, I recommend 150, 200, maybe 300 feet in between your sensors, almost half the distance that you would on ductile iron and cast. This may involve then, if you're in a typical city street environment where you have two sensors at the intersection at your mainline valves, or two sensors on your hydrant valves, you may need to cut that distance in half. And you can do that by, if you have meter pits available to you, or curb stops available to you, you can place a sensor at a meter or a curb stop to cut that distance in half. But again, what you're trying to do is trying to have those sensors capture the sound. And in order to get pinpoint and correlation, you need to have at least two of those sensors capturing the sound. So that's a good question. Another question is, can we set the sensor directly on the pipe? Absolutely, absolutely. We say valves and hydrants simply because they're the easiest things to access. Um, but there's nothing wrong with setting a sensor and placing it directly on the pipe. Many times when you have a long length of pipe and you don't have access to valves, you may need to core bore down to the pipe to place a sensor directly on the pipe. Um, that is absolutely acceptable. Um, and actually a great way to get close to the leak. I also mentioned too that the pipe diameter does play a role in how far that sound travels also. As the pipe diameter gets larger, the mass of the pipe, the amount of pipe material is greater. And the more mass of material, that also absorbs the energy of the sound traveling down the pipe. So as that pipe diameter gets to the larger sizes, and I'm talking, 24 inches, 30 inches, 36 inches, that is going to greatly impact how that sound or how far that sound is traveling down the pipe. So as your pipe material gets to larger distances, you need to be mindful of that with your placement of the pipe. And one of the things with a large diameter, hydrophones, which is another listening tool, a sensor, a style of sensor. A hydrophone is a sensor that isn't placed directly on the valve, but is wet tapped into the pipe. Not only is that sound being carried through the pipe network via the pipe wall, but that sound also travels through the water column in the pipe. With a set of hydrophones, your hydrophones are a sensor, but instead of sensing the vibration on the pipe, they're wet tapped into the pipe, and thus they are sensing the vibration or the sound through the water column. Sound travels fantastic through the water column, and thus you can you're better able perhaps to monitor and to do your leak detection on those large diameter pipes or those long transmission mains. Particularly if you have long plastic transmission mains, you have with limited valve access that must be monitored. In many cases, with those long, large diameter plastic transmission mains, hydrophones are, in most cases, the best option. Also, too, the back pressure, the water pressure, your pipe system will greatly impact how well your leaks are sounded. If you have a very low pressure system, that is going to shrink the pressure differential between the water inside the pipe and the water escaping outside the pipe. When you're doing your leak detection surveys, you need to, if you have the ability to increase that pressure differential, that is going to help your leak detection activities. If you have a pressure sustaining valve down the line, perhaps that sustaining valve can be reset to increase the back pressure behind the valve, and thus you've created a better environment for your listening to occur. Also with us today, I'm going to put him on the spot. I think Steve Gilliam is with us. And Steve has been, I think, chatting with the folks in the chat, answering some questions. Max, can we get Steve online here? If he had any particular questions that he wanted to address, we can certainly introduce Steve. We're trying to, there's some great questions coming in through the chat, and we want to use our last few minutes, 10 minutes wisely. So if there were any specific questions that Steve was dealing with, I'd like to welcome Steve to jump in here and answer any of those questions.
Yep, Steve, you're unmuted if you'd like to introduce yourself.
Thanks, Matt. Hi, Eric. Hi, everyone. Yeah,
Hi.
Steve. I'm Steve Gilliam. I'm with Goodman. I am the technical support director for the company. And yeah, I just see a couple of the questions in front of me here, Eric, towards the end that I can answer. One is how to sync data from two sensors. Well, that's done. The sensors themselves have a clock inside them as such. So when they're programmed, they get a timestamp from the device that's programming them, and that could be anything from an Android device to a server, or however they're being programmed, whether it's fixed network or portable equipment, or if it's a real-time correlator, they're being synced from their actual device that's communicating with them real time. But basically they're getting a time stamp, so they're recording sound at exactly the same time. If they're recording sound at exactly the same time, they're able to correlate and pinpoint the leak. Another one we have here is, how do you choose whether to use hydrophones or accelerometers? Excuse me. Well, hydrophones should be used if, like Erica said earlier, on very, very large transmission trunk mains where your access points may be very far and few between. It may be, maybe 500 meters up to a kilometer between access points. And so because of that, with an accelerometer that sits on the outside of the pipe, the sound traveling along the internal wall of the pipe might not actually get that far. But the sound traveling through the water column can travel a lot further. And so generally you're going to be using hydrophones when your distance between access points are very long and the pipe diameter is very large. And like Eric says, you've got a lot of thickness of wall material in these large diameter pipes. So again, the sound dissipates very quickly. So large diameter pipes, long distances, hydrophone should be used. And also really on plastic pipes. Again, if you don't have access points that are really within 100 meters, then again, you should really be using hydrophones. But on your normal basic distribution pipes where you have plenty of valves, plenty of hydrants, accelerometers should be fine. Okay, Eric, over to
all right.
you.
Okay, thanks a lot, Steve. And we've put our contact information on the screen in front of you. If you have any questions, please feel free to reach out to us. We are doing quite a few of these webinars. We have very specific product webinars, demonstrations of actual products that are available to be viewed. We're recording and putting a lot of these webinars up on the internet for you to come back and watch at your leisure. So I think that's wrapping up. I got to thank you. So you're quite welcome. Again, thanks a lot to everyone. The water loss group. The folks at Guterman. Max, thank you. Steve, thank you very much. It was an absolute pleasure. I apologize for the weak internet connection today, but hopefully we were able to work through that, and I've gotten some good comments from that things sounded good. So once again, my name is Eric Galosi. On behalf of everyone at the Guterman family, we were absolutely pleased that you can join us today, and we're happy for you to be here. I hope you learned a little bit something from our Leak Detection 101 webinar. I'm signing off. Thanks a lot.